Got it.
Okay.
Okay. All right.
Cool.
Okay. I guess I'm
Yes, very
ready.
good.
Yep.
So it's my pleasure to introduce Sylvia Shu, I guess.
Yep. That's fine.
Um, and today she will present results from her recent paper from March of this year on the prospects for detecting the Axion annihilation signal using continuous gravitational wave surges. I guess mainly LIGO and Virgo.
Yep.
Cool.
Thanks. So I think, let's see. I'm wondering if I should have my face. It doesn't matter. Okay, I'll hide my face. All right. So yeah. So thanks for having me here. And thanks for the introduction. Just to preface this, I am a data analyst who currently works on gamma rays. Previously worked on gravitational waves. So today I'm going to be talking about how we could directly detect axions or sort of bosons in general using gravitational wave searches. And what I've linked to the paper that's on the archive right now, as well as the repository where we have uploaded and provide some of our simulated data, which I'll discuss a little bit soon. So to start off with, I need to figure out how to go to the next slide. That's not how I do it. There we go. So to start off with, I think this probably is familiar to many people, but just to give a bit of an overview. So how do we get these axions to annihilate? Well, we need them to form enormous clouds around black holes. How do we do that? We invoke the superradiance instability. So this is a phenomenon by which particles around a black hole can extract some of the spin of the black hole to increase in number. The classical analog to this is if you have a rotating cylinder and a ball that grazes by the cylinder. Depending on the relative speeds of the ball in the cylinder, the ball can pick up some velocity and can increase in energy and momentum as it goes by. Now, of course, in the classical analog, the ball flies off to infinity, but for the superradiance instability, the key difference is that this particle, this boson, is now trapped within the gravitational potential of the black hole. And so this quickly becomes like a runaway process, and you could very quickly build up large numbers of bosons existing in the vicinity of these black holes. So at the end of this, then, you might have what you can think of as a gravitational atom, which is sort of similar to the, it has some similarities to the classical atom, but now we have a black hole and then a cloud of bosons surrounding it. And this cloud, because these are bosons, this cloud can be as, can have occupation numbers as high as 10 to the 78 particles, for instance. And again, because they're bosons, they can all occupy the same state. And what I'm going to be focusing on today is the fastest growing level. So for the gravitational atom, there are also well-defined energy levels. And so I'm focusing on the fastest growing one. And similar to the classical atom, there is this, what we can call a fine structure constant, where that defines the properties of how this cloud grows and then how the cloud emits gravitational waves. And these properties, this alpha term, is defined only by the combination of the black hole and boson masses. And here's where I'm going to get a little bit hand-wavy, but if the particle does not have a very strong self-interaction, then or self-coupling, then this cloud grows stably. And at some point, there are enough particles in the cloud that they start to annihilate. And as they annihilate in the presence of the gravitational potential, of the gravitational field, then what you can get are two bosons annihilating into, let's say, one graviton. And in this context, then, the frequency of the gravitational wave or the graviton that's emitted almost entirely depends on the mass of the boson. So for the most part, then, the gravitational wave frequency that comes out just depends on the mass of the boson that has formed this cloud around the black hole. And just to note that so the black holes and the boson, so the bosons that can couple to the black holes, A particular boson, a given boson can couple to a wide range of black hole masses, but the rates will really be maximum if the size of the black hole is similar to the Compton wavelength of the boson. So let's see, what is my next slide? Yes, so with all of this, you can get, okay, you get bosons annihilating into gravitational waves, great. And the frequency of the gravitational wave just depends on the mass of the boson, great. They're bosons, they're all in the same state. So what you get is coherent gravitational wave emission at a single well-defined frequency. And these are known as continuous gravitational waves. And there's something we already search for from using gravitational wave searches. And now all we have to do, or one thing we can do, is take our search results and reinterpret them in this boson annihilation framework. So these gravitational waves that I'm talking about now, these continuous gravitational waves, they're a bit different from the ones that we have detected so far. The gravitational waves that we've detected so far are transient signals that occur when two compact objects, so neutron stars or black holes typically, when two compact objects merge. These can last for, these can be detectable by the current set of detectors for about a minute to less than a second, depending on the properties of the compact objects. What you see on the right here is a figure from the, I think this was from this was from the very first gravitational wave signal that was detected in 2015. And in this figure, let's see, my mouse shows up. Yes, in this figure, the vertical axis is the strain, which is the fractional length, the fractional change in length that is measured by the detector as the gravitational wave passes through. So the gravitational wave passes through, and it actually changes the length of, let's say, of one of these detector arms. And based on these changes and based on how these changes occur, how large these changes are, you can then work backwards to figure out properties of the original system. So what I show on the left here, so on the left down here is just a sort of theoretical example of what one of these waveforms might look like, where the amplitude depends on the properties of the two, of the two masses, for instance. And then there's this frequency that kind of changes, that gets smaller, that gets frequency that gets smaller, larger, frequency that gets larger, wavelength that gets smaller, that this depends on just how rapidly things are orbiting. So these are the types of signals we have detected so far, but of course there are other, just like electromagnetically, we don't just detect transient signals, we also detect continuous or persistent signals. We would also expect to detect continuous persistent signals of gravitational waves. And traditionally, we have expected these signals to be from things like lumpy neutron stars, because all you need is just something very massive and, let's say, dense that's slightly non-axisymmetric. So it could be, for instance, a neutron star with a little mountain or a little bump on it. And then when you have this type of system, then you have continuous gravitational waves, because this neutron star is existing for a very long time. The frequency is very steady, so it's at a single frequency because it's just rotating very steadily. And the frequency is dependent on depends on how fast it's rotating. And then the amplitude of these signals, or the characteristic strain, the amplitude just depends on properties of the neutron star. So I'm going to digress a little bit, talk a little bit briefly about neutron stars, just to show you the sorts of what we currently do in continuous waves, and then move on to talk about how we can apply that to the interpretation in the boson or axion annihilation framework. So these signals that we want to detect, these continuous signals, are many orders of magnitude weaker than the transient signals that we have already detected. But because they're at well-defined frequencies, what we can do is we can just search over a long period of time. Theoretically, the noise will average out while the signal will become more and more significant. So the sensitivity, though, so how likely are we to detect these signals depends on a lot of things. It depends on how strong the signals are, but it also depends on how sensitive our detectors are, of course. So the current generation of gravitational wave interferometers, there's a handful around the Earth. The ones I'm focusing on today are going to be LIGO Hanford and LIGO Livingston. which are the two LIGO detectors in the US. There's also Virgo in Italy and Kagra, which is starting operations in Japan. What you're seeing on the left here is a figure that gives you an idea of how sensitive the detectors are at different frequencies. So the three different curves here correspond to three different detectors, the two LIGO detectors in Virgo. And you can think of this vertical axis as a measure of sensitivity, as a measure of sort of how much the detectors inherently wiggle at these different frequencies. And if the detector inherently wiggles a lot at this frequency, then it's going to be harder to detect a signal at that frequency. So a smaller number indicates increasing sensitivity. It indicates that you're more sensitive to smaller and smaller changes in space-time, so smaller and smaller strains. And the shape, just a little brief digression, the shapes of these curves depends on a lot of different things. So there's a sort of an envelope that depends on kind of broad properties. So for instance, there's part of this, there's a contribution from thermal noise. So right, so this is going to cause some jittering or some movement in your system. There are also these lines right here. There are also these sort of peaks. These are at individual frequencies, and these are lines that can be caused by things such as the violin modes of, so basically the resonance modes of your suspension. So in all these systems, you have a lot of mirrors and a complicated suspension pattern. And just like in violin strings, when you pluck a string, there's a resonance frequency. Similarly, there's a resonance frequency for all these suspensions. Let's see. Okay, so digression aside, what does my next slide look like? Right. So depending on what frequency you're looking at, right, you can see it could be more or less difficult to dig out a signal from the noise. So how do we actually dig out and find these signals? In theory, this should be relatively straightforward, right? If you have, let's say, a rotating neutron star with a bump, the waveform at the source is pretty straightforward. It's a sinusoid. It's a sinusoid that has a specific frequency, and maybe it's slowly spinning down, so there's a frequency derivative or maybe multiple frequency derivatives. But you take that sinusoid and you Fourier transform it, and you should just get a single peak in frequency. Of course, in real life, that's not that simple, because in addition to because the Earth, right, is orbiting, so you have and then the Earth is rotating, and it's also orbiting around the sun. So all of this extra motion creates a Doppler pattern, a Doppler modulation pattern, right? So this Doppler modulation pattern will change the frequency that you're detecting or that you're looking for from your source. And this Doppler modulation pattern is different for every single point in the sky. So in reality, what you have to do for your searches, or one thing you can do for your searches, is to not only try to not only Fourier transform, right, and find the peak in frequency, you also have to account for the different Doppler modulation pattern at the points in the sky that you're interested in. So depending on what you're looking for, of course, this can get very computationally expensive. And this computational cost, as well as this question of what are you interested in, will help determine what kind of search you want to do. So there are a couple of different searches, different large categories of searches that we often do in searches for continuous gravitational waves. So on the one hand, you could run a targeted search where you search for gravitational wave emission from a known pulsar. So this is a source where you know exactly where the object is in the sky, and you know exactly what the frequency is. So you basically just have to search one point in parameter space. This is very cheap, and you can run a very sensitive search over one single source. Of course, the problem is, then at the end of the day, you just have information about that single source. If you want to go one step further, or one step more general, you could run what we call a directed search. These are searches for gravitational wave emission from known neutron stars. So for instance, what you might do is look at a supernova remnant, and in the middle of the supernova remnant, you might have an X-ray source that you're pretty sure is a neutron star. But because it's not pulsating, You don't know how fast it's rotating, so you don't know the gravitational wave emission. But you do know there's a neutron star at the center of your supernova remnant. You might know it's relatively young, and so maybe you have a better chance of detecting gravitational waves from this. Of course, you know where it is in the sky, but you don't know what frequency it's at. You have to search a wide frequency range. And with both of these types of searches, though, you're just running searches over individual sources. So far, I think we know of about 2,000 neutron stars in the galaxy. There's estimated to be around 10 to the 8, 10 to the 9 neutron stars in the galaxy. That's a lot of neutron stars we don't know about because most of them are dim. They're beyond our, they're too dim for us to detect currently. They're non-pulsating, or maybe they're just, the pulsations are just not pointed at us. So what you can run then is an all-sky search where you sort of make minimal assumptions about what you expect. And of course, this greatly increases your computational cost. And also, has some, you take a hit on search sensitivity, but then at the end of the day, you can say something about the entire sky rather than about individual sources. So moving back now to, so these are a couple of the different types of searches we do for continuous gravitational waves. How can we apply these search results to look for, or to interpret this instead in terms of the boson annihilation framework? So the first thing to notice is that the targeted search doesn't really make sense here, right? Because for a targeted search, for the neutron stars, the targeted search where you know the source position and you know the frequency. This doesn't make sense for the boson annihilation search because here this assumes you would know what black hole you care about and what mass your boson is at. This, of course, is one of the big questions, because there's a wide range of masses that these axions, for instance, or just bosons in general, could exist in. So instead, if you have a known black hole and you want to test an unknown or a wide range of bosons, then you could run a directed search. So this could be, for instance, searches around the, you could search for the annihilation signal from the black hole that is produced at the end of a merger. So for instance, the first merger of two black holes in 2015, the very first merger we detected, that left a remnant black hole that's quite heavy, and we have some idea of how fast it's spinning, and we know exactly how old it is, and so that could maybe be a good maybe be a good target for running these searches. This is a little bit distracting, right? And this paper I've linked to here, EC et al., this is exactly what they have done. They have run a search they have looked into a search, and run a search for the boson annihilation signal from this one particular heavy, rapidly rotating, massive black hole. Of course, the problem is that with a given black hole, you are sort of limited to a relatively small range of bosons that you could theoretically detect today. It's because, as I said before, the rate of the superradiance rate is really maximized if the sizes of the boson of the black hole are similar. So this, even though it gives you a wider range of bosons you can test, it still kind of limits the mass range. So what we're left with then is an all-sky search where you make minimal assumptions on the black hole positions or on the boson mass. What I've linked to here is a recent paper that presents upper limits from an all-sky search and then interprets them based on just some arguments based on a few example systems. So that sounds great. So this is maybe the most powerful tool that we have for looking for the boson annihilation signal, or at least interpreting null results. But we can, we can actually, so the important thing now is to try to figure out, well, how can we interpret, let's say, null results? We have an idea, so let's see. We have an idea now for, we're not actually starting from nothing. We have an idea for where black holes, or how black holes are distributed in the galaxy. So we can make some predictions based on where the black holes are, or where we think black holes are. We can make some predictions about what we expect the annihilation signal to look like from all the black holes in the galaxy, right? So now we don't just care about one neutron star or one black hole. We can try to predict the signal from all the black holes as an entire group. So what we want to do then is, theoretically, we would want to, best case scenario, we'd want to detect the particle. But if we don't, if we don't detect the particle, we would want to take some upper limits on the gravitational wave signal strength, for instance. How can we translate that into a range of disfavored boson masses? So what I'm showing on the left here, and I'll show it larger soon, but for instance, this is a set of recent results from all sky searches, where on the vertical axis you have this upper limit on strain, so upper limit on the gravitational wave signal strength that we can detect. And then on the horizontal axis, you have frequency, a signal frequency. And so this sort of has a similar kind of shape as those detector sensitivity curves I showed below, because, right, how sensitive you are really has to do with how sensitive your detector is at the different frequencies. So how do we get from our measured upper limits to something more concrete, like a range of disfavored boson masses? So we need to, first up thing to do then is to characterize what we think, or characterize how these signals might look like. So any individual signal, as I said, depends mostly, the frequency of an individual signal depends mostly on the mass of the boson, so about twice. So the gravitational wave frequency is going to be, what's that word? Proportional to, thank you, is going to be proportional to twice the boson mass to leading order, although there's going to be a few percent correction depending on things like how massive your black hole is, because with a more massive black hole, that's going to sort of, one way to think of it is sort of gravitationally redshifting your signal, right? So depending on how massive your black hole is and a little bit how fast it's spinning, that's going to change the gravitational wave frequency slightly. So as I said before, a lot of these properties depends on properties of the not only the formation of the gravitational atom, but also the gravitational wave emission depends on this fine structure constant alpha, which is a combination of the boson mass and the black hole mass. So if we, and I should say that in all our studies so far, we're focusing on spin zero particles. So we're focusing on scalar particles here. For these types of particles then, the gravitational wave emission, so the H0, the strain at its peak, so at its loudest is going to be proportional to alpha to the 7th. So if you have, for instance, a heavier black hole or a heavier boson, you can theoretically get louder signals. And so the first thing to do is say, okay, well, are these signals loud enough for us to detect? How loud would they be from black holes in the galaxy? So what I'm showing you here is as a contour plot of this value H0 peak, so the signal strength. This is for systems of black holes that range from 5 to 30 solar masses. So this is pretty representative of black holes that we expect to find in the galaxy, as well as a range of boson masses. And this range is chosen so that the signal that comes out is in the right frequency range to be detectable by LIGO and Virgo. So for a lot of these, because this peak H0 is dependent on alpha to the 7th, so such a large power of alpha, you can range, the peak H0 ranges over many orders of magnitude. And if we compare this now to some recent all-sky search results, where at its most sensitive, the detectors can detect signals with H0 values of around 10 to the negative 25, well, you can see then, I lost my mouse, doesn't matter. You can see then that for much of this parameter space, we are talking about signals, at least at their peak, that are orders of magnitude louder than the detector sensitivities. So these are signals that would be much high above the noise and would be theoretically very easily detectable. Of course, it's not as simple as that, because when you have louder signals, that means the particles are annihilating more quickly, basically. And so that also means that your signal is going to die down more quickly. So the rate at which the gravitational wave signal dies down can be described by this time scale tau, and this time scale is proportional to alpha to the negative 15. So as soon as you have a louder signal, you also have a much shorter signal time scale. On top of that, remember there is this requirement that in the classical analog, there's this requirement that with the ball and the cylinder, in order for the ball to pick up speed, it has to be slower than the cylinder. The cylinder has to be faster than the ball. Similarly, in order for the cloud to grow, the black hole spin has to be faster than a certain critical amount, or a certain amount, this chi-c. So this chi-c is also depending on alpha. And so when you have larger values of alpha, you also require faster spinning black holes in order to build these clouds in the first place. So this combination of factors makes it non-trivial to predict what the expected signal is from a population of black holes in the galaxy, because this population has has a wide range of spins, and has a wide range of masses. So just a couple examples now so to put some numbers to these properties. So on the left, you see the same panel before is a contour plot of the signal strength. In the middle, this is a plot of the signal duration. So this is in years. So this is a measure of how fast the signal decays. And this also covers many orders of magnitude, from larger than a Hubble time to less than a year. And on the right, what you have is a contour plot of whether the system forms in the first place. So the minimum spin the black hole must possess in order for the system to form at all. And you can see that if you have a system of, let's say, a heavier black hole and maybe a lighter boson, where the signal is fairly loud at birth, this signal has a strain of maybe a couple orders of magnitude higher than our noise floor. The problem is that the signal decays at a rate of, the time scale is around 1,000 years or so. So the signal quickly drops off over the orders of over thousands and thousands of years, and so you're relatively unlikely to be detecting the signal today. And same thing if you go to, for instance, heavy bosons and light black holes. So you really need to simulate what happens to an entire population with all of these different properties in order to get a handle of what you expect to be able to detect from boson annihilations. So this is what we did. We took a range of boson masses, and this range again is determined by what we can measure today using LIGO and Virgo, let's say. And with this set of boson masses that we have, for each boson mass, we calculated its interactions with a population of 10 to the 8 black holes in the galaxy. So, and then from there, we get out a prediction of what the signal looks like for that particular boson mass. And then we do this for this entire range of boson masses. So what we need now is a prescription for for the properties of 10 to the 8 black holes in the galaxy. Of course, we don't actually know where the black holes are. We don't know what their properties are down to a T, but we can make some simulations based on some educated guesses, or based on observations and observational evidence. So what we did was we started with a prescription for where black holes are in the galaxy today and how fast they're moving. And we did this by saying that, okay, we have 10 to the 8 black holes. They're born in the disk and the bulge of the galaxy in certain percentages and with certain formation rates. When the black holes are born, they're born with some sort of initial velocity. This is a combination of the bulk velocity in the disk, which is just rotating, and the bulge, which has sort of more of a randomly distributed velocity. And the black holes also are also imbued with a natal kick at birth from whatever asymmetries exist in the supernova explosion that produces the black holes. So the black holes are born, they have an initial velocity, and they're born at certain times, and then they move through the galaxy for the rest of their life until today. And they, in particular, they move through a combination of the gravitational potentials of the disk, of the bulge, and also of the halo. So we take these black holes, and at the end of this prescription, we have 10 to the 8 black holes with positions and velocities and ages. Of course, we also need to prescribe for them masses and spins. And so what we did was we started off with just a few sets of distributions for these. So for masses, we chose a power law distribution, so a salpeter distribution. We said the minimum black hole mass is around 5 solar masses, and the maximum could be around 20 or 30 solar masses. These are consistent with simulations, with modeling of formation of black hole formations in the galaxy, and also consistent with what we have observed so far from black holes in the galaxy. And we also tried a couple of different distributions on the initial spin of the black hole. This is more unknown, this is more uncertain than the black hole mass distribution. So we chose, for instance, let's say an optimistic spin distribution where it goes from 0 all the way to maximally spinning. And then we chose a more moderate distribution where it goes to maybe 0.5, and then a pessimistic distribution where all the black holes are rotating relatively slowly. So what this gives us then is a combination. So what this gives us is a prescription for where black holes are, how fast they're moving, and how massive they are, and how rapidly they're spinning. With all this information, we can combine this our boson mass with our 10 to the 8 black holes for every single boson mass, and we can get, for instance, plots that a plot like I'm showing on the right here. So this is for a particular boson, a boson with a particular mass, so 4 times 10 to the negative 13 eV. What you're seeing on the vertical axis, this is the characteristic strain H0, so this is a measure of how strong or how loud the signal is. On the horizontal axis is the gravitational wave emission, or sorry, the gravitational wave frequency that we observe at the detector. Now remember, because everything is moving, this is not just the frequency at the source. This also takes into account the fact that the black holes are moving, that the black holes are traveling with, and so you get a little Doppler shift from the black hole's motion itself. So each of these dots here is the gravitational wave signal from a single black hole boson cloud system. Now this is just the tip of the iceberg, right? Because we have 10 to the 8 black holes, and so there are going to be many systems that are too weak because they're too far away or alpha value is too small for us to be able to detect them. So what the horizontal orange line here is an approximate a cutoff for the approximate current search sensitivity. So this is how sensitive searches are right now, or all sky searches are right now for continuous gravitational waves. What this means is, roughly speaking, any dot that appears above this horizontal orange line, we have a very good chance of detecting. So we did this for a wide range of bosons, and so here what you're seeing is this type of plot for 4 different boson masses across the range that we're interested in. So starting from the lightest part of our mass range to somewhere that's 10 times heavier than that. So for all of these, again, each dot represents the signal from a single black hole boson cloud system. This is the annihilation signals. For all of these, the vertical axis is the strength, the characteristic strain, so how strong the signal is, and the horizontal axis is the frequency that we would observe at the detector. And for all of these, the horizontal orange line is the approximate search sensitivity at that frequency. So remember, this depends on what frequency you're at. There's some parts of the detectors that are more sensitive than others. And so you can quickly see that even going from so looking at the first 2 plots, even just doubling the boson mass, you quickly go from having very few signals that would be detectable to having many signals that are over an order of magnitude louder than your noise floor or than your search sensitivity at that frequency. Now, of course, as you go higher and higher in frequency, you don't necessarily get louder and louder signals, right? This is because a lot of these signals that would be loud are also the ones that are decaying more quickly, and so the shape of the overall shape of this set of signals also depends then on what what boson mass you're looking at, and this will change as you go from very light bosons to heavier bosons. You can also look at the properties of, and this is what we did. We looked at the properties of the black holes that produce these signals. So what you're seeing in the second set of panels, so these correspond to the boson masses. These correspond to the boson masses that are shown up above. In each of these plots, in each of these panels, the vertical axis is still the strain, the gravitational wave strain. The horizontal axis is now the distance, or how far away the black hole is from Earth. And the size of the circles here corresponds, or gives you an idea of how massive the black hole is. So bigger circles correspond, bigger and darker circles, bigger bluer circles correspond to more massive black holes, and smaller, whiter circles or more transparent circles correspond to lighter black holes. And this, so you can see that if you start out with light bosons, all of those signals are coming from massive black holes. So this really depends on the higher end of your mass distribution. Whereas when you go to heavier and heavier bosons, you're getting more signals from farther away, but those signals are all coming from lighter black holes. So from the lighter end of your mass distribution. So at the end of this, so we basically did this for a wide range of boson masses. And then what we did was we took these horizontal orange lines, these search sensitivities, and said for each of these boson masses, how many signals show up above these orange lines? So if they show up above the orange lines, then they are detectable. And we started off with, so we studied 5 different black hole distributions. So where the maximum mass is either 20 or 30 solar masses, and where the maximum spin is either 0.3, 0.5, or 1. And if you look at our distribution where, what we call our sort of nominal distribution, where the black hole mass is, the maximum mass is 20 solar masses, so this is relatively conservative, and then the maximum spin is 1, so this is relatively optimistic. What you can see is that there is a range in here of boson masses going up to around, let's say, 2 times 10 to the negative 12 eV, where you would, using our black hole population, you would expect to see at least tens, if not hundreds, of signals in your all sky searches for continuous gravitational waves. So there's a wide range, or there's a range of boson masses where these signals should be fairly easily detectable. Of course, that also depends on that depends greatly on what you believe about your underlying black hole population, right? So if you go to moderate spins, so if you say the maximum black hole spin is 0.5, so these are the gray squares now, the number of signals you can expect to detect goes down by an order of magnitude. This is because it just gets harder, right? Because there's a minimum spin that the black hole has to have in order to form the cloud in the first place. So with slower and slower spinning black holes, it becomes harder and harder to form these clouds, and fewer of these clouds form. Then if you drop that down even further, so if you look at the gray triangles here, the maximum spin is only about 0.3, and so black holes are born very slowly spinning on average, then you would only expect to see a handful of signals maybe in a small range of boson masses, and so it becomes very difficult to say anything it becomes very difficult to say anything about most of the boson mass range. Of course, then you could go to heavier black holes. So let's say you believe that black holes in the galaxy go up to 30 solar masses instead of 20 solar masses, which is still reasonable. The interesting thing is that if you invoke heavier black holes, you can get more signals. You can get many more signals for lighter bosons, right? So you get more signals if you have a lighter boson, but then very quickly you don't gain any more from those heavy black holes. Right, this is, remember, because with heavier black hole, you also get larger values of alpha. That means that your time scales get shorter. That means that your signals stop being detectable much quicker. And so with heavier black holes, you gain in this sort of small range of boson masses, of the lighter masses, and you don't necessarily gain more signals in with the heavier bosons in this range. And so you can play this game with, what we did was we took this and we looked at 5 different black hole populations to predict the number of signals that come from boson annihilations for these populations. Now, of course,
Spoiler, we haven't detected anything yet. I mean, we've been searching for continuous gravitational waves for a while, under different, for different types of signal sources, and we haven't detected anything yet. So if we continue to not detect anything, then what can we do to take our upper limits on the gravitational wave signal strength on the strain, and how do we interpret this into a range of disfavored boson masses? So the stepping stone we need in the middle then is some sort of expectation on the number of detectable signals. And this is what we've done here. We've predicted the number of detectable signals keep in mind that we've only done this for 5 different black hole populations. And you might not, you might not believe us when we say these are plausible black hole populations in the galaxy. And so this is where, this is sort of where our paper ends. And this is where I'm going to start speculating about what we can do in the future, what we might do from now on. So how do we interpret null results given that you might have a different black hole population that you're interested in? So you might start with a set of priors on the black hole mass or the black hole spin that's different from what we had. And this gives you a prescription on the population of black holes in the galaxy that, again, is different from what we had. So what we were doing was we were going from this prescription of 10 to the 8 black holes and then directly calculating the expected number of signals. But that's very computationally challenging. One thing we could do, again, this is sort of speculative, one thing we could do as a possible plan is to, let's say, divide this population of black holes into smaller discrete bins. And each bin could be a certain range of black hole masses and spins, for instance. And we might produce a set of gravitational wave signals for a certain bin of, let's say, heavy black holes, and then a bin of medium black holes, and then a bin of very light black holes. And then depending on what you believe the black hole mass distribution looks like, for instance, you could sample from these sets of population, these sets of signals, to produce your own set of expected, to produce your own plot figure for the expected number of signals for for your own black hole population. So this is, again, a little bit speculative, and there's a lot of details that would need to be hammered out, but this is a way I can imagine, or we can imagine, going in the future. And this is just, again, I'm just flashing on the screen here, not flashing, showing on the screen here a link to the paper that's on the archive currently, as well as, again, the link to a file that contains these boson signal populations that we have simulated that you can play with yourself. All right, thanks.
Cool. Thank you very much for this very interesting talk.
Thanks.
I think I at least learned a lot about gravitational waves now.
Okay, cool.
I just have a few questions I didn't really understand. So if this signal that you're looking for is so confined in a certain frequency range, how can you disentangle that from these spikes in the intrinsic noise? Or how do you know that those spikes were intrinsic noise in the first place instead of already a signal from black hole superradiance?
Yeah, that's a really good question. This is one of the things that plagues us in general. So let me see if I could, just to show. So this is referring to the fact that, yeah, the detectors are noisy, and that some of this noise are exactly spikes at particular frequencies. So there are a couple of things we can do. There are some searches that are good at removing these spikes. The thing is that these spikes appear at single frequencies. They always appear at certain frequencies, whereas an astrophysical source, for instance, will vary in frequency because of the Doppler modulation pattern in the sky. So there's some searches that are good at removing the spike, discounting the spike already because it doesn't quite fit with the astrophysical Doppler modulation. There are other searches that remove it after the fact by looking for this modulation. Does that make sense?
But wouldn't that require that you
Go ahead.
know where the signal comes from, or so? Do you need to have a sense of the direction of your signal, or?
So the not quite, because so you don't, right, it's a good question. So you don't have to know exactly where the signal is coming from, right? Because any signal is going to have a Doppler modulation pattern that is non-zero.
Mm-hmm.
But anything that comes from that comes from a terrestrial source, so anything that's at the detector will have a Doppler modulation pattern of 0. So what you're doing is you're saying, well, does this look like something that has a Doppler modulation pattern of 0, or is it non-zero? If it's 0, if there's no Doppler modulation pattern as you're running your search, then you can do things like, say, okay, I'm pretty sure then this is going to be actually a detector artifact, or this is going to be one of these lines in the detector rather than an astrophysical signal.
Cool. Yeah. And I think that makes sense. Could you? I mean, I'm mainly concerned about these even lighter bosons, this fuzzy dark matter, or from the very start was wondering if you could use supermassive black holes from other galaxies then even and redo this analysis, or if the signal would just be too small for detecting axions of, I don't know, 10 to the minus 18 EV or so.
Yeah, absolutely. That's definitely sort of the next obvious or the next the best extension that we could do, right, of this type of thing. So if you go to much lighter, and I don't have the numbers, but I know other people have done these predictions. If you go to much lighter bosons or axions, then you go to supermassive black holes, and then you could what you need then is a gravitational wave search that is sensitive to much longer wavelengths or much smaller frequencies. And so what you need then is for LISA, you need to wait until LISA launches. So that's going to be the space-based gravitational wave detector with much longer arms that's going to be sensitive to much smaller frequencies. But you can, and actually you can, I don't have a good handle for how strong these signals would be. But in that case, one thing you can do right now, actually, and one thing that people have been doing with supermassive black holes, we also have some measurements of how fast those are spinning. So you can already set some constraints with some assumptions on certain boson or axion mass ranges by looking at how fast the supermassive black holes are spinning. The fact that they're spinning, right, because as the clouds grow, then extract spin from the black hole, so the black hole slows down. And so if you see a very rapidly rotating supermassive black hole, that kind of suggests that there probably hasn't been a cloud around it that's been extracting its spin. So you can do some sorts of limits or sort of these sorts of regions based on how fast these supermassive black holes are spinning. And you can do something similar for stellar mass black holes as well. But of course, the tricky thing is that those also come with a set of assumptions. So it's sort of a complementary way to set constraints on these axion existences.
Oh, cool. Does it make sense to, or how different would it be if you include, I don't know, self-interaction, if we actually assume the QCD axion or whatever, that doesn't make sense to also look for self-interaction or things like that, or is the effect too minimal for that?
So this is let's see, what can you, okay, this is slightly out of my wheelhouse. What is this referring to? Okay, actually, yeah, can you rephrase, but with on a slightly dumber level?
Okay, so this now assumes that the boson only interacts gravitationally, right?
Yes, I believe so, or primarily, yeah.
Primarily. And maybe we both are not the right people to ask that, but how sensitive would that be to a non-gravitational potential, to some self-interaction or so?
Okay. I think so. This is my the short answer is probably someone else might be a better person to answer this. But my understanding is if in that case it would be very difficult to really form the cloud to its sort of full, to as big as it could be, right? So what often would depending on how strong these self interactions are, what could happen is instead of fully forming this cloud, the cloud could then collapse into and then produce what's known as, I think, as a boson-nova. Right? And then so what you get is then again a flash, a short burst of gravitational waves. There actually are searches that look for unmodeled transient signals, so unmodeled bursts of gravitational waves. And I don't have a very good handle for how strong these signals are expected to be or how frequent they would occur. But you could imagine looking for a different, using a different type of gravitational wave signal to put some constraints on that type of particle.
Cool. I think we should wrap that up here.
Yep.
And postpone any further questions then to the talk. So thank you very much. And I'm looking forward to seeing you then next week.
Okay, thanks. How do I